Hey everybody, we're going to be talking about electrons today, but in a lot more detail in terms of where they are found around the nucleus. So far we've discussed, single electrons and how getting them to move from their position in the nucleus and then come back to ground state creates light. We're going to actually be taking a look at all the electrons around a nucleus now in a particular atom. So they have a pretty organized system in how they set up, and there's a number of reasons for that, which we will talk to as we go through. But today, hopefully by the end of it, you will understand how and where electrons are set up and found around the nucleus. So just a quick history. We've talked about this, but a review here. So the plum pudding model was thought to be the model of the atom for a long time. And remember, that model said that atoms were solid and they had made of solid material, and then they had these negative bits throughout it. And then Rutherford came around with his gold foil experiment, and he realized through that experiment that the nucleus was, the solid mass in the center was actually pretty tiny, called that a nucleus. That was positively charged, had protons and neutrons in it, and then electrons were found around the outside of the nucleus. And that most of that space around the nucleus was empty. There was nothing in it. So these electrons fill in within that empty space around it. Niels Bohr came in a little bit later and said that electrons were on these circular paths that went around the nucleus. So the electrons were circling around the protons and the neutrons. And that's the model that you probably learned about in middle school, because that's the one that is pretty accurate in terms of where they thought these circles were located. But we now know, because of Heisenberg and a whole bunch of math, that electrons are actually found in these spaces, or we call them electron clouds, around the nucleus. So instead of being on a fixed path, they're actually within a space or an area around the nucleus. And that's what we're going to talk about. So how are these clouds organized? So we have what are called energy levels. This is the distance away from the nucleus. So if you're in the first energy level, you're the closest to the nucleus. If you're in the second energy level, you're next closest. Right, so think of the nucleus as being the front desk of a hotel lobby. And if you're staying on the first floor of the hotel, you're closest to that nucleus or that desk. If you're on the second floor, you're a little further away. And then if you're on the third floor, you're even further away. So each energy level represents a little further out away from the nucleus. So if we think of the hotel or a house, and where people are staying, the higher the level, the further away from the nucleus you are. Within the energy level, so within the floor of our boarding house or our hotel, there is called a sub-level. So our floors can be broken up into separate individual sub-levels. So that would be like if you are staying in your hotel and you are in, say, like Nicolay, they have an F wing and a D wing and a C wing, right? It represents a little bit more about where you would be situated or organized. So if you were staying in a room called, F205, like my room, you would know to come upstairs to the second level away from the nucleus, and you would be in this upper hallway. The same if you were in D wing. You wouldn't come upstairs by my classroom because that's F wing. You would be located over in the D wing. So those are sublevels within an energy level that helps narrow down where that electron position can be found even further. And these sublevels have kind of shapes to them. So the 4 different sublevels we're going to learn about means that The space that they can be found in could be spherical or almost look like a balloon or a barbell shape. So that means that that electron floats within that area of that shape. We are going to call those the kind of the type of room. So within your sublevel, you could either have an S or a P room. And we're going to call those sunny and pink because it just makes more sense than some of the scientific jargon. So you could be on the second energy level in an S room or a sunny room. Or you could be on, say, the third energy level in a P room or a pink room. So this is just narrowing down, again, where that electron can be found. The 4 sublevels that exist are called S, P, D, and F. Those are the only 4 options. Those are the 4 areas or shapes that can be found within an energy level. Then lastly, we can narrow it down even further. So within those sublevels, we can actually narrow down where an electron is, and we call that an orbital. So think of that, if we were talking again like our hotel room, that would actually be like the bed within the room. So, you know, sometimes the electron is hanging out and sleeping, and then sometimes the electron gets up and moves, maybe goes and uses the bathroom or sits on the couch or looks out the window. So the electron can be found within that room or that sublevel. But in our hotel, you know, generally you go there and you get a room and that's where you sleep, and then you get up and can walk around the next day. But most of the time you're going to be found in that bed, right? So the beds are what we call the orbitals, okay? So we have an energy level where the electron can be found. Within the energy level, we've narrowed it down in a sublevel. So that would be like which wing you're in or which type of room you might be in. And then in the sublevel, we've narrowed it down even more to what's called an orbital. And that would be the bed within the room on the floor. Each orbital can hold only up to 2 electrons. Sometimes there's 1, sometimes there's 2, no more than 2. And the reason for that is because they are negatively charged. So electrons don't like to be near each other. So they will only fit 2 in these tiny orbital spaces if there's no other place to go, right? Otherwise, they like to repel and stay away from each other as much as they can because they're very negative. The other thing you'll sometimes see, and this isn't going to be so important for us, but if you take AP chemistry or you go into chemistry in college, they'll oftentimes talk about the opposite spin. So electrons are constantly moving, and again, because they're negative, when they get near each other, they repel, and they actually end up moving in opposite directions from each other. So they will spin opposite. And that's all you pretty much need to know about that one. So, how do we fill in electrons around a nucleus? We have these energy levels, we have these sublevels, and then we have these orbitals. Like, okay, what does that mean, Winkle? So, there are actually only 3 rules for filling in electrons. First one is called the Aufbau principle. It's the name of the guy that came up with it. And he said that electrons will always fill in around a nucleus, filling the lowest energy level first. So in our hotel, the first floor always gets filled up first before they would start filling in on the second floor. Then Hund came up with the Hund's rule, and he realized that you only put 1 electron in each orbital, so you only put 1 in each of our little rooms before you would pair them up. So that goes back to the being negative and shoving them in these small spaces. You only want to put 1 in each bed or in each orbital before you would start putting the second electron in. And I'll show you what that looks like in a minute. Then the third rule for filling is called the Pauli exclusion principle. And that says you can only put 2 electrons per orbital and they will have opposite spin. Okay? So, Next slide is a little confusing, but I think once we go through the rest of the notes, you'll be able to come back to this and it'll make a little more sense. But this is what the outside of a nucleus looks like. You can have up to 7 energy levels. So that's what we know exists so far. There are 7 total floors or energy levels around the nucleus. Within those energy levels, there are sublevels. Notice that the first energy level only has one sublevel, S. The second energy level only has 2 sublevels. There's an S and a P. The third has 3, and then the 4th, 5th, 6th, and 7th have 4 sublevels, S, P, D, and F. The number of rooms within the sublevel also vary. So any S sublevel has 1 room to it. Okay, so it's a pretty small space. So the first energy level with its 1 sublevel S only has a single orbital that can be filled in. Once that's full, it would then go to the second energy level and you would start filling in electrons there. You have sublevel S and P. S still only has 1 orbital. P always has 3 orbitals. So if you follow through and you look at each sublevel, you can make sense of what can be found, right? So S, P, and D can have up to 5 orbitals, and then F can hold up to 7. So 1, 3, 5, and 7, S, P, D, and F. If we can fit 2 electrons in each orbital, what that means is if I have 4 orbitals, how many electrons could I potentially fit in the second energy level? You would take 4 times 2, so you could have 8. How many electrons could we potentially fill the first energy level? Well, we've got 1 orbital, so 1 times 2 electrons means I could fit 2. Our third energy level has 9 total orbitals. So if it's 2 electrons per orbital, 9 times 2 is 18. And then 32, 32, 32, 32. Okay? So again, this might be a little confusing, but let's take a look at a different way to view this. So this is called an orbital diagram. Okay? And in this orbital diagram, we have a representation of our nucleus here at the bottom. And then these numbers, letters, and dashes represent energy level, sublevel, and orbital. So here's my first energy level. I have an S sublevel, and here's my orbital. I can fit up to 2 electrons on there. And then the next is our second energy level. I've got an S and a 2P. So I've got 2 places here that I can fill in electrons. Notice I'm going to fill from the bottom towards the nucleus, and I'm going to move up and fill in electrons based on whichever energy level and sublevel comes next. Okay, that's important, so I'm going to say that again. You start by the nucleus and you work your way up and you fill in whatever energy level and sublevel comes next. And the reason I say that twice is because the numbers don't always mean lower. And I'm going to show you what I mean by that. Let's see if I can get a little, trying to see, hang on one second. Okay, so we're just going to use the arrows we have up here. So starting down at the nucleus, I need to pick an element that I would like to represent here. So I am going to pick beryllium, Be. So if I look up beryllium on the periodic table, it has an atomic number of 4. So that means it has 4 protons, which means it also has 4 electrons. So I'm going to fill my 4 electrons on what we call an orbital diagram, because I'm showing all my orbitals here. And I'm going to use little arrows, and I'm going to put them in from lowest up till I'm done. So I need 4 total electrons. Okay, so I'm going to stick 1 here in my 1s. And then I'm going to put my second one right next to it. Okay, so I've got 2 electrons filled in my 1s. I go up to my next line or orbital, and that's the 2s one. And I'm going to put my electrons in here. So I'm going to put one. Oops. And then I'm going to put the other one. So notice I have arrows representing electrons. I put one in, and then I filled in with the next one. I have a total of 1, 2, 3, 4 electrons. And therefore, that is called the orbital diagram for beryllium, Be. Okay, so let's pick something like oxygen. Okay, oxygen, if I look at the periodic table, has an atomic number of 8, which means it has 8 protons and 8 electrons. So if I asked you to draw the orbital diagram for oxygen, I've already got 4 of my electrons in, 1, 2, 3, 4. So now I need to go up to my next fill in. So that's right here, my 2p. And I need to add 4 more. So check this out. I am going to notice I'm going to put 1 in each orbital, because remember, they don't want to be near each other, right? So they're going to go into separate quote-unquote beds or orbitals because they want to stay as spread out as possible. So I have 1, 2, 3, 4, 5, 6, 7. So I only have 7 electrons. So this would be nitrogen. I'm looking for 8. So I need to now add 1 more. So this is what I'm going to do, is I'm going to add my last electron in that first orbital. So kind of think of it as you have to fill up all your lines in the level before you can pair them up. So fill up before you pair up. So if I count my arrows, I've got 1, 2, 3, 4, 5, 6, 7, 8. This is the orbital diagram for oxygen. Okay. If I were to do one more, let's say, let me get up to, let's do calcium. So calcium has 20. Okay, so you have to be a little patient with me. I need to put in 20 arrows. So let's, I've got 2, 4, 6, 8. I'm just going to paste a bunch here. Paste a bunch. So if I am going to do calcium, okay, so calcium has an atomic number of 20 with 20 electrons. So I have 2, 4, 5, 6, 7, 8. I need to start filling in 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, we're almost there, 19, and 20. So notice, you guys, I went from 3p, the next level I jumped to is 4s, right? And then I would go to 3d. So you literally fill up from the nucleus up. Ignore the numbers in the front. So sometimes you're going to fill in a 4 before you fill in a 3. It literally depends on whatever is lowest or closest to the nucleus. That's where you fill. Once it's filled, then next I would go to 3D and I would fill these in. And then I would go to 4P. And then I would go to 5S. And then 4D and then 5P. Okay? So Aufbau principle, the rule says start from the nucleus and fill in up, and then fill one before you pair up, and then once it's full, you move on to the next level and you give them opposite spin. Okay, so last thing I want to talk about today with notes is so these are clunky, right? They're big and there's arrows and it's a great visual and it shows you how to fill in your electrons. But scientists don't want to run around handing out these orbital diagrams to represent where electrons are found in an atom, right? So we're going to stick with our calcium example here. So we have our arrows filled in, and I'm going to show you how we can write this in a much nicer format for electrons around a nucleus. We call this format electron configurations. Okay, and this is how it works. You're, again, going to start with your very lowest one that you filled in, which is 1s. So I'm going to type 1s. And then I am going to tell how many electrons are in my 1s. So there's 2. And you make that as an exponent. So it's 1s, it looks like 1s squared, but really it's just 1s with an exponent representing how many electrons are in that sublevel, which is 2. Okay, so then I go up to my next level. I have 2s, and how many electrons do I have here? I have 2. So I make a little 2. Next level up is 2p. So I type 2p, and in this sublevel I have 2, 4, 6 electrons. I move up to 3s with 2 electrons. Then I go to 3p with 6, 2, 4, 6. Then I go up to 4s, which is my last thing I had to fill in, and there are a total of 2 electrons. Okay, this is what we call an electron configuration. Okay, so this is kind of the code for where the electrons can be found around a nucleus. Oops, sorry. Okay, so 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. That's the electron configuration. Now, you guys, check it out. The really cool part about this is I can test and check and make sure that it is the element that we were working on, right? So we had originally said that this was calcium. So I'm going to make sure we all know it's calcium. So I'm going to type that in here. I'm going to actually make it a little bigger so we can see it. And I'm also going to bold it so that when you come back to this later and you're studying or whatever, you know. Okay, so this is my calcium atom. And to check it out, I'm going to add up all the exponents. So I have 2 plus 6 is 8, plus 2 is 10, 16, 18, 20. If I look at the periodic table, the atomic number for calcium is 20, which means it has 20 protons and 20 electrons. So this is correct. I'm also going to double check my arrows. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So this is my symbol calcium. This is my orbital diagram, which shows the arrows. And then this is my electron configuration, which shows the code or how you would write out where the electrons are found around an atom. If I go back and do, let's say, looking at a periodic table here, let's say I want to go back and do nitrogen. So that has 7. So I'm going to get rid of some of these arrows. So just be patient with me a second. Okay, so nitrogen has 7 valence electrons. If I look at the periodic table, not valence, I'm sorry, 7 electrons. It's got 7 protons, so it has 7 electrons. I filled in my orbital diagram, 1, 2, 3, 4, 5, 6, 7. So to do my electron configuration, I'm going to type out what, starting from the nucleus, I have 1s2, 2s2, and then my last level is 2p, and I have to count how many electrons. 1, 2, 3. So I do a quick check. I add up my exponents, 3, 4, 5, 6, 7. I look at my arrows. I have 2, 4, 5, 6, 7. I check the periodic table. N is 7. So this is my orbital diagram for nitrogen, and this is the electron configuration, or the code for where the electrons can be found. So I hope this was helpful. You guys are going to go finish up your POGL that we started last time, called electron configuration POGL. So go back into Canvas and finish that up, and you will hit submit. Thanks.